If you're building modern applications, you've felt this tension. I know you have.
Oh, absolutely.
On one side, you have these incredibly powerful large language models. I mean, they understand human intent with just startling accuracy.
Right.
And on the other, you've got your real enterprise architecture, the robust, structured, live Java services that actually run your business
And for too long, those two worlds have been totally separate.
in complete isolation.
That isolation is the exact wall that, well, that we're here to talk about tearing down today.
Okay.
Welcome to the deep dive. We're focusing on something called function calling. It's really the technical breakthrough that finally bridges that neural network to the runtime environment.
So this is the bridge.
This is the bridge.
Yeah.
Our mission here is to take you through the architecture, the flow, and maybe most critically, the implementation. And we're going to use the really elegant, developer-centric approach of the Spring AI framework to do it.
That's great because we're looking at some excellent source material here, all focused on mastering Spring AI function calling.
Right,
And the goal is exactly that mastery.
right.
We want you to really get how to turn an LLM from, a passive question answer into a fully active agent.
One that can perform tasks.
Yes, in your actual business systems.
Yeah.
We're looking at how you give your AI agent, hands and feet by connecting it seamlessly to your existing Java services.
And this isn't just about, plugging in an API endpoint. It's about setting up a real standardized, secure dialogue between that messy, unstructured human language and your structured executable code.
So it's the mechanism.
It's the mechanism that turns a natural language request into a specific typed service invocation.
Okay, let's unpack this architecture then, and let's start right with the problem itself. Why is this bridge even necessary? Let's jump straight in and tackle that central paradox. LLMs are brilliant, but they're completely isolated. The amount of knowledge inside an LLM is just. It's vast.
Yeah.
It's all derived from petabytes of data scraped from the internet, from books, public repos.
All of it. But for all that historical understanding, the models are, for all intents and purposes, frozen in time and space.
That's the paradox, isn't it?
That's it, precisely.
Yeah.
They have this near encyclopedic knowledge up to their last training date, but they're fundamentally disconnected from the live dynamic state of the world.
Especially the world inside your company firewall.
Exactly. They are trapped, metaphorically inside this computational box.
So can you break that down? What does that isolation mean in, practical terms for a business application? What are the specific knowledge gaps we're talking about?
The gap is all about latency and accessibility. I mean, an LLM can probably tell you the average temperature in New York for the last decade,
Sure.
but it absolutely cannot tell you the temperature there right now.
Okay.
It can explain the entire concept of inventory management, but it can't check the current stock level in your database.
Because that would require a live query.
It requires executing a live query, interacting with a proprietary system, retrieving data that was generated moments ago. The LLM just can't do that on its own.
So if I ask an LLM, do we have 10 of product X left in stock? It might give me a response that sounds really helpful,
It'll sound plausible, yeah?
but that response is just based on statistical patterns from its static training data, not the actual current state of my database.
Exactly. The response is, linguistically plausible, but it's completely useless for making any kind of operational decision.
Right.
We're talking about systems that are just blind to the critical real-time context. Things like user-specific permissions, live database records, external API data that changes every second.
The current state of the Kubernetes cluster, for example.
All of that. And the cost of constantly retraining and redeploying these massive models just to keep up with millisecond changes, it's astronomically prohibitive. I mean, even if it were architecturally possible, which it really isn't.
And it's not just about passive access to information. Our source material really highlights an even bigger limitation for building real AI agents, and that's the inability to perform actions.
Correct. And that's the key difference between instruction and execution. The LLM can understand a natural language command that shows an intent to act, but it has no mechanism, no I/O capability to actually execute that action in an external system.
So give us those concrete examples again. What can this isolated LLM not do, even if I ask it to, very clearly?
It can't execute commands. It can't book a meeting in your calendar on the Exchange server.
Nope.
It can't call a proprietary financial service to make a transaction. And most relevant to our scenario today, it can't create or update a structured resource in an internal system.
Like posting a JSON payload to a post-app tickets endpoint?
Exactly. To create a new customer record or facilities ticket, it just can't do it.
So if the user says, book me a flight to London next Tuesday, the LLM can give me a perfect summary of what the flight booking process looks like.
A beautiful summary.
But it can't actually open my Java application, find the booking service bean, and call the bookSlite method with the right parameters.
That's it in a nutshell. Our sources use this really powerful analogy. The LLM is trapped inside a box, and these external arrows, requests like select from users or structured API calls, they just hit the outside of the box. They can't get through that computational wall to activate the real systems like the database or your cloud services.
So the neural network's power is kind of confined to just processing text.
It has no hands. It can't reach out and manipulate the application environment.
And this isn't just about, missing a library or something. It's a core architectural separation.
It is.
The LLM is designed for language prediction, not for the secure, audited execution of enterprise code. That separation is really important.
It is. It's critical. We need a secure, reliable, auditable, and structured bridge.
Yeah.
A dedicated mechanism that can translate that messy, unstructured intent into a reliable, structured call.
One that ensures only trusted, application-controlled business logic ever gets executed.
Yes.
Which, that perfectly sets the stage for the breakthrough. How do we build that bridge and finally unlock the box?
This is where it gets good.
This is where the architecture really shifts in a big way. Function calling. It's not just another feature, is it? It feels like a fundamental design pattern that solves this core problem.
It is. The core concept is, it's elegant, but it's architecturally profound. Function calling is a mechanism that allows the LLM to request the execution of your application-defined functions.
Request it.
Request it so it can interact with the outside world. This mechanism is what turns the LLM from a statistical predictor into an intelligent router.
Okay, I want to pause on that distinction you just made because it feels critical. The LLM requests the execution, but it does not execute the code. Why is that so important, especially in a secure enterprise Java environment?
It's the entire foundation of the security model. If you just allowed the LLM to execute arbitrary code, you would face just unimaginable security and stability risks. Natural language is messy, it's adversarial, it's prone to all kinds of injection attacks. By limiting the LLM to only generating a structured request, a recommendation for an action, you keep full control over the execution environment.
So the LLM gets to decide what needs to happen, but my Java application decides if it can happen, how it happens, and crucially, under whose authority it happens.
Precisely. Your application logic, which is already secured with authorization layers, input validation, transaction controls, that is the only thing that ever executes the actual business logic.
So the LLM is the brain, formulating the intent.
And your application is the audited, controlled set of hands that performs the action.
That makes function calling an architectural necessity then, not just a convenience.
Okay, let's walk through the full detailed flow. The user, the LLM, the application logic. Let's connect them all with this bridge. This 5-step process is really the heart of this whole deep dive.
It is, and the choreography is complex, but the beauty is that the Spring AI framework hides that complexity from you.
Okay. Step 1. Step 1. The user prompt. This is just the natural language command that expresses intent. It's unstructured, often ambiguous. Our example is perfect. The coffee machine on the second floor is broken.
And the application receives that prompt and just sends it straight to the LLM.
Right. Which brings us to step 2, LLM analysis. This is the moment of intelligence. Now, critically, the LLM has already been told about the tools, the functions that it has available.
We'll get to how that happens in a bit.
You will, but for now, just know that the model processes the user's intent, it matches that intent against its library of known function definitions, and it determines that the best way to satisfy this request is not to generate text, but to invoke an external function, like create ticket.
So it's making a proactive choice to use a tool that it knows about.
Absolutely. Which leads directly to step 3, function request. Because the LLM knows it needs to take a structured action, it stops generating conversational text. Instead, it generates a strict structured output. And this output is always a JSON object.
Always JSON.
Always JSON. And this JSON specifies the function name it wants to call and the required arguments, which the model has painstakingly extracted from the user's messy natural language prompt.
So for the coffee machine, it would translate that sentence into what exactly?
It would generate something like function name, create ticket, arguments, location, floor kitchen, description. The display is off and it's leaking water.
Why is the JSON structure so important here? Why can't the LLM just output a text instruction like, hey, create a ticket.
Because JSON provides a strict machine-readable contract. Natural language is always ambiguous, but JSON enforces a schema. It ensures predictable argument names and types.
So for the Java app receiving it.
For the receiving Java application, getting a JSON payload means it can be parsed reliably, it can be validated against a schema, and it can be mapped directly to your Java method parameters.
It takes the guesswork out of it.
It completely eliminates the need for your application to try and reinterpret the LLM's output. It establishes a necessary, auditable data contract between the AI brain and the application's hands.
Okay, so that structured JSON request then hits the application, and that triggers step 4, application logic.
Yes. Spring AI intercepts and parses that JSON payload. It finds the function name, which is create ticket, it validates the arguments, and it invokes the corresponding local Spring Bean, your existing trusted Java business service.
This is where the real work happens.
This is the real work, the database transaction, the API call to JRA, whatever it is. The function executes and generates a concrete result, like a success message and a ticket ID. Maybe ticket T123.
And now we get to that critical pivot point.
Yeah.
The result has to go back to the linguistic brain, back to the LLM.
Exactly. Step 5, LLM response. The application sends the result of the function execution back to the LLM. This is the crucial second half of the conversation.
Right.
The LLM processes this result. It integrates that new real-time fact ticket T123 into its linguistic context. And only then does it formulate the final contextualized human-readable answer for the user.
Something like, understood. I have successfully created ticket, hashtag T123 for the broken coffee machine.
Exactly that.
That two-step trick. Yeah. Back to the LLM. First for the request, and then again for the result. That seems key. What would we lose if the application just took the result from step 4 and responded directly?
You'd lose all the linguistic precision and the conversational flow. If your app just spits back, ticket T123 created, it sounds robotic. It's disconnected.
Yeah.
The LLM makes sure the response maintains the right tone. It references the original context, the broken coffee machine, and it provides a satisfying conversational confirmation. It manages the whole narrative thread, so the system feels like one coherent agent, not two pieces of software just duct taped together.
Okay, before we jump into the Spring AI implementation details, I want to clear something up. You mentioned real-time data access earlier. A lot of developers are using retrieval augmented generation, or AG, for that. Isn't function calling just RAG for live data?
That's an excellent and really necessary distinction to make. They serve fundamentally different purposes, even though they both involve external data. Our RAG is designed for passive knowledge retrieval. Its goal is to go fetch unstructured or semi-structured information like documents, PDFs, knowledge-based articles, and then inject that text into the LLM's context window.
So the model can generate a more informed answer.
Exactly. Our RAG is about providing context for a conversation.
And function calling.
Function calling is for active execution and structured data retrieval. It's not primarily about ingesting text. It's about invoking executable application logic. If you need to know the weather, you call the getWeather function. If you need to update a database, you call the updateRecord function.
So the key difference is the output. A RAG gives you text snippets. Function calling gives you a strict JSON command for execution.
Precisely. If you need to know what our internal policy manual says about facilities reporting, you'd use RAG.
Right, yeah.
If you need to create a facilities report, you must use function calling.
That makes perfect sense.
Yeah.
RAG deals with what is the answer, and function calling deals with what structured action must be taken.
Exactly. You need function calling whenever the answer requires interacting with live state or executing real business logic. They are complementary, but they are functionally very distinct.
Okay, that clarity really helps anchor the whole thing. Now we understand the complexity of that 5-step flow. So how does Spring AI make that incredible orchestration feel simple for a Java developer?
That's the magic.
Okay, let's unpack the developer side of this.
Yeah.
We just described what's basically a 9-stage internal loop, if you count all the back and forth communication.
It is.
If a developer had to manually handle all the JSON parsing, the function dispatching, the state management, the two-way API calls, I mean, it would be boilerplate hell.
It would be brittle, time-consuming, and just so prone to error. I remember building similar kinds of workflow routers, 5 or 6 years ago, before frameworks like this existed. It was all custom JSON marshaling, tons of reflection just to match arguments. It was a mess.
And Spring AI's goal is to abstract that away.
Completely. It sticks to the core Spring philosophy. Let the developer focus only on the business logic.
So what's the core model that Spring AI gives us?
The genius of it is leveraging the existing familiar Spring paradigms. The function you want to expose to the LLM, your tool, is just defined as a standard injectable Spring Bean.
Okay.
And crucially, it often implements the java.util.function interface, which, defines a method that takes one input argument and returns one output argument.
So we're not learning a whole new set of AI interfaces here. We're just taking existing, proven Java functional patterns and applying some metadata to them.
Exactly, you define the contract. Input type is your request record, maps to the apply method's input. Output type is your response record, maps to its return value. And the great part is the business logic inside that function can be anything.
A REST call, a JDBC query.
Anything. As long as it's a Spring Bean, Spring AI can see it.
But the LLM isn't built to read Java interfaces.
Yeah.
So how does Spring AI teach the LLM what the function can do?
This is where that magic annotation comes in. This is the API documentation for the LLM. It's the @description annotation.
Okay, walk us through the role of @description.
So you place the @description annotation directly on the function bean itself, and it just contains a natural language string explaining the function's overall purpose.
And that's what Spring AI sends to the LLM provider.
That human-readable string is what Spring AI uses to generate the function definition schema that it sends to OpenAI or Gemini or whoever.
So if I make a bean called weather checker, the LLM doesn't see that name. It sees the description. @description retrieves the current weather conditions for a specified location, including city and state.
That's the API contract that matters to the model. The LLM uses that text to perform step 2 of our flow, the analysis step. It matches the user's intent. What's the temperature in Boston? Against all the @description strings it knows about.
So you're effectively writing your API docs, not for a human developer, but for the neural network itself.
That's the inversion. It's so powerful.
So what's happening under the hood to make that work? How does Spring AI turn this friendly Java bean into the strict format that the LLM API needs?
It's a lot of reflection and introspection. When your application starts up, Spring AI scans the context for all the registered functions. It uses reflection to read the method signatures, the argument types from your Java records or POJOs.
Okay.
And then it combines that textual @description with the structure it derived from the method signature to build a formal JSON schema, usually something that adheres to the Open API specification.
So the framework is dynamically generating this function schema, the documentation of our function's inputs and outputs, and it sends that machine-readable schema along with the user's prompt.
Correct. The developer only writes the Java logic and the natural language description. Spring AI handles all the technical translation required to register that function with the remote AI service.
Which means your Java code becomes the single source of truth for the API contract. That's huge for maintenance.
Immensely.
Okay, so let's go back to the seamless integration part. What specifically does a developer not have to do because Spring AI is handling the heavy lifting?
They avoid handling the entire conversational state machine. Once the LLM decides to call a function, Spring AI handles, let's see.
Give me the list.
1, it intercepts the function request JSON. 2, it validates that JSON against the schema it sent. 3, it parses the JSON arguments and deserializes them into the right Java record.
Okay.
4, it invokes the standard Java method on your bean. 5, it captures the return value. 6, it serializes that return value back into JSON. And 7, it manages the second API callback to the LLM to send the result for synthesis.
That's as a list of 7 orchestration steps that are completely managed by the framework just by calling one chained method on the chat client.
Yes.
That turns what could be weeks of custom JSON handling and brittle API work into, what, an afternoon's work.
It allows the Java team to focus purely on the functional contract, making sure the business logic inside the function is solid instead of worrying about all the plumbing just to talk to the AI API.
To make this all tangible, let's really dig into the use case from our source material. Building an AI service for facilities management ticket creation.
This scenario is perfect. It really encapsulates that whole transformation process. Taking messy, unstructured human input and turning it into a perfectly structured, executable system command.
Which is the goal of agentic AI.
It's the whole point.
Okay, let's start with the raw input. The user prompt is, the coffee machine in the second floor kitchen is broken. The display is off and it's leaking water.
So rich in detail, but it completely lacks the strict formatting a ticketing system needs, right? The system goal is to invoke a function, create ticket, with 2 very specific structured arguments.
Location, second floor kitchen.
And description. The display is off and it's leaking water. The LLM has to intelligently parse, categorize, and extract the user's intent into those specific parameters.
And the final goal, the final AI response, is a professional confirmation that the action was taken. Something like, understood. I've created ticket hashtag T123 for the broken coffee machine. A technician will be dispatched.
And we get there through 3 distinct implementation steps in Spring AI.
Let's start with the foundation, the code that actually does the work.
Step 1. Expose Java logic as a Spring Bean. Okay, so we create a standard Java class, maybe facilities ticket function, and it implements function create ticket request, create ticket response.
So you're enforcing that strict contract for input and output.
Right away. We mark the class with @component, make sure it's exposed as a @bean in the application context.
And then the crucial part, the metadata.
Absolutely crucial. We attach the @description annotation to that bean definition. For this use case, the developer writes, @description, create a ticket for a facilities issue in the ticketing system.
And that one declarative sentence is what tells the LLM, hey, I can handle requests about creating facilities tickets.
Exactly. It needs to be accurate, concise, and really cover the function's full utility.
So step 1 basically wraps the actual service call, which could be anything, a SOAP endpoint, a microservice, and gives it a purpose statement for the AI.
Precisely. Now, step 2 is where we guide the LLM's intelligence. We tell it exactly how to parse the user's intent into specific arguments. This is the step that I think a lot of developers overlook when they're new to function calling.
And that is step 2. Model the function's data contract. This is defining the create ticket request and create ticket response records.
The structure is simple, right? Java records with fields like string location and string description. But just naming the fields isn't enough.
Why not?
Well, if we just name the field string location, the LLM might struggle to differentiate between, say, the city the user is in and the actual physical location of the broken coffee machine in the office.
Ah, okay. And this is where that second vital annotation comes in.
Yes, @JSON property description. So while @description is for the function's overall purpose, @JSON property description describes the specific purpose of each input parameter.
So this is the detailed user manual for the LLM's argument extraction logic.
That's a perfect way to put it.
So give us the concrete examples for our create ticket request.
Okay, for the location field, we would annotate it with a JSON property description. The specific building, floor, or room location of the issue, variable third floor kitchen or server room A.
That's super specific.
It has to be. That instruction guides the LLM to extract second floor kitchen and distinguish it from any other context. Then for the description field, we might use @JSON property description, detailed summary of the problem focusing on symptoms and visible damage.
Which ensures the LLM captures the display is off and it's leaking water, not just is broken.
Right. That level of specificity is what ensures the LLM generates a reliable, structured JSON object in step 3 of the flow. We're essentially programming the argument extraction layer through this structured metadata.
It feels like we're optimizing the prompt that the LLM uses internally for extraction.
That's exactly what's happening. If a user prompt was really ambiguous, like, say, the screen is black, and we had strong @JSON property description annotations that required a device in app, the LLM might internally prompt itself. Okay, the user said the screen is black. I need to call diagnose issue, device ID, which needs a device ID. The user didn't give me one, so I have to respond conversationally and ask the user for that device ID.
That is a fascinating insight. The clarity of the @JSON property description actually helps the model handle missing or ambiguous input by steering it towards asking a clarifying question instead of just guessing.
Absolutely. The better your documentation, the more reliably the model can perform argument extraction and error handling.
Okay, so step 3 brings it all together in the application service layer.
Step 3, enable the function in your chat client. This is the line of code in your Java app that kicks off the whole workflow. When your REST controller gets the user's HTTP request, it uses the ChatClient.prompt builder.
And what's the minimum choreography you need in that builder?
It's a really clean chain. You have to provide the raw user input, so .user message. And then crucially, you have to explicitly register the available tool for that specific conversation turn.
So function, create ticket.
Exactly. And finally, you trigger the execution with .call.
So why do you have to explicitly call .function, create ticket every time? Why doesn't the chat client just know about all the function beans that are available?
Well, Spring AI does know about all the beans in the context, but you might not want every tool available for every single prompt.
Oh, right.
Explicitly registering the function with .function name lets you dynamically control which tools the LLM is allowed to use in that specific context. You could base it on the user's session, their authentication level, or the broader application state.
So it's a context-specific security and relevance control mechanism.
Exactly. And that full execution chain chatclient.prompt.usermessage.function create-ticket.call, that one line now fires off the entire multi-step process we analyzed before, all of it orchestrated by Spring AI behind the scenes.
Okay, let's reinforce this. Let's walk through the entire 9-step sequence one more time, really highlighting Spring AI's role at the transition points.
Yeah, let's do it. This is the full life cycle of a single user request. Step 1. The user kicks it off with that unstructured command. Coffee machine on second floor is broken.
Step 2. My controller packages this up, identifies the right tool, and invokes the chat client, chatclient.function, create-ticket.call, and this hands off control to the Spring AI framework.
Step 3. Spring AI prepares the payload. It takes the raw user text and the dynamically generated function definition, that open API schema it built from our @description and @JSON property description annotations, and sends this complex instruction set to the remote LLM.
So the LLM gets both the prompt and its tool inventory, and it recognizes it needs to act.
Step 4. The LLM responds to Spring AI, but the response isn't text. It's that structured function request JSON payload with the function name and the extracted arguments. Location, second floor, description, coffee machine broken.
This is the moment. Unstructured language becomes structured data.
That's the transformation. This JSON hits Spring AI, proving the model successfully interpreted the intent and got the details.
Step 5.
Spring AI intercepts this JSON, deserializes it into our Java create ticket request record, and invokes the local create ticket Spring Bean. This is where your actual Java business logic finally executes.
Step 6. The facility service does its thing, updates a database, calls a legacy system, whatever, and it returns the result. A small response record with a success confirmation, T123.
Step 7. Spring AI serializes this result back into a JSON object and performs that crucial second API callback to the LLM. It's basically showing the LLM the outcome of the action it requested.
So now the LLM is fully informed. It has the original user context, the request it made, and the factual successful result.
Step 8. The LLM synthesizes the final conversational output. It generates that human-friendly text confirming ticket, #T123, making sure the tone and context are just right for the user.
And finally, step 9. The controller receives that final synthesized chat response from Spring AI and returns it to the user. That is a massive amount of architectural complexity managed across 2 systems and multiple API calls, all abstracted down to a single Java method chain.
The elegance of it it's just undeniable. It really shows how Spring AI acts as this sophisticated translator and conversational state manager. It ensures all that heavy lifting of linguistic interpretation and structural conversion is handled completely away from the developer's core business logic.
I think it's worth pointing out the reliability implications here too.
Yeah.
Because the framework is strictly enforcing that JSON schema in step 5 and relying on robust Java types. We gain so much reliability compared to just trying to parse unstructured text output. We go from hoping the LLM generates the right format to relying on predictable, strong typing.
Absolutely. The reliance on structured typed inputs, those Java records, and the annotations that define the schema, that's what makes this enterprise grade. It gives developers the confidence that the model is making an audited, predictable call against a known contract.
So, okay, what does this all mean? We started with the LLM trapped in its box, limited to static knowledge. We used function calling, facilitated by Spring AI, to give that intelligent brain access to real-time data and actionable services.
The transformation is complete.
It feels like it.
The ultimate outcome is the birth of the active agent. We've shifted the role of the LLM from just explaining the world to actively participating in and manipulating the enterprise environment.
So let's summarize the 4 big benefits this architectural shift delivers, especially for our Java developer audience.
Okay. First, connect to anything. Since the function is just exposed using a standard java.util.function, function interface, and dependency injection, you can integrate the AI with literally any internal service, legacy system, database.
Any external API that your existing Java infrastructure already supports.
Anything. The LLM can now call anything your Spring application can call.
Okay, second benefit. This unlocks real action and automation.
Oh, we move decisively beyond just conversational Q&A. These agents can now perform complex tasks. They can initiate transactions, create structured records, escalate workflows, manage external devices. It allows for entirely new automation layers in customer service and internal tooling.
Third, it provides real-time awareness without that costly retraining.
Right. By routing requests through live functions, the LLM is empowered with up-to-the-minute data from your sources. It's no longer limited by its training cutoff date. It has instant, secure access to the current state of your business.
And fourth, and this is the critical one for our audience,
Huh?
it's truly developer-friendly.
It is. We get all of this incredibly complex orchestration using standard familiar Spring paradigms, the declarative nature of annotations, simple functional interfaces, dependency injection.
There's no steep learning curve with some complex AI tool library.
It's just Spring doing what Spring does best.
Yeah.
The fact that developers can achieve this level of AI-driven complexity by just focusing on writing clear, descriptive metadata with @description and address and property description, while the framework handles all the serialization, the network calls, the conversational state, it's revolutionary.
This has been a really deep and, I think, very rewarding dive into the architecture of modern AI integration. It really shows how intent gets translated into execution.
And if we connect this back to the bigger picture, this whole mechanism fundamentally changes how we view our enterprise codebase.
How so?
It's no longer about just querying a model for information. It's about empowering the model to dynamically navigate, interpret, and act upon your existing enterprise architecture.
That raises a final, provocative thought for you to carry forward then. Consider the implications of every legacy Java service. I mean, services that might have been around for a decade or more, suddenly becoming discoverable and callable by natural language intent.
That shift means that every well-defined Spring Bean is now a potential programmable action for an intelligent agent. This isn't just about writing better chat interfaces.
No.
It's about making your entire enterprise environment, every single function defined by your developers, accessible and programmable through an intuitive, natural language interface.
So the LLM becomes the unified